parametric and methods, it's really important that we start to really understand the characteristics and quality of the sites beyond what we can see, because often with the intention of design is that we are trying to make the world a better place. And the best way we can do that is to really advocate for the things that the general public, stakeholders, and decision makers can't actually see, right? Because as cliche as it sounds, out of sight, out of mind, right? So part of it is revealing these things that we don't often commonly see. And, you know, I was very fortunate that a lot of the work I'm about to show you was really kind of a building on of some of these existing precedents, right? The work by Edward Tufte and understanding how to communicate data. During my thesis studies, Nadia had a huge influence on my work as well, specifically the exposed city, another kind of concept of how we start to map those invisibles, and even some of the work by Bradley Cantrell, and really thinking about not only about seeing these systems, but how are they actually interacting together to create different outcomes. You know, I'm a little frustrated that they stole this line from me, because this is often what I preach with my own students, and this is my whole philosophy. You know, with graphic visualizations and representations, it all comes down to telling a story, right? It's really about how you can start to really sympathize with, again, your clients, with stakeholders, with the general public, all these communities that are in need. And, you know, you really want to make sure that they kind of are, that they're considered, right? That their needs are being met. And so, you know, when you're trying to, whether it's find funding, whether it's trying to get more support, you really have to be able to tell all the elements of the story. And, you know, we already use different drawing typologies to tell different stories, right? Every type of drawing has a purpose, right? The plan drawing is intended to really talk about the spatial organization of program and circulation. Section drawings show the respect to the ground plane, the manipulation, giving a sense of depth. And then also it, sorry, it shouldn't be elevation, but it should be perspective drawing, showing spatial and atmospheric conditions of a space as well, right? So each drawing tells a different story. And, you know, we see this example of how, you know, all these different ways in which we do site analysis, right? Whether it's analogous, digital, or computational, the thing that really bothers me about seeing this type of work is that you can see that regardless of the methods that were used, it's still giving us the exact same outcomes, right? We're still seeing sun patterns, we'll still see these wind directions, distance circles. All the information is the exact same, even though they're using completely different methods. And I find this honestly a bit of a travesty that, you know, our technology is advancing, our methods are becoming more comprehensive, yet we're still showing the same exact information. And I firmly believe that if we are going to advance in our technology and our methods, our design thinking has to evolve in tangent with that, right? We can't just continue to tell the same kind of conventional story, even though every other tool is out there to help us improve and show something much more robust and comprehensive to that. You can see here, this is the kind of site analysis that I have my students doing, right? It still has that same framework and foundation of looking at things like slope and sun and lighting and wind, yet it's still showing something that's a little bit more relative to the specific site, those programs and needs, right? All that information is still there, but it's just looked at a little bit more comprehensively. It's starting to, again, compile all this information and producing different outcomes. And I think, you know, a common thing that happens in the design process is that we often latch on to this convergent way of thinking, right? Having some type of preconceived solution to a problem. And we kind of drive our methods and direction towards that solution. However, my belief is that, we look at the problem, or we discover the problem, and we look at what are all the different types of outcomes or scenarios that can help solve that issue, right? So I think that's a huge way of thinking about it, is let the problem present to us the solution instead of trying to contrive something that might not be appropriate, might not be sensitive, and in the end probably won't even be successful. I think we have to really think about what the problems are that we face in today's society, right? Whether it's specifically related to climate change and all the things that are resulting from that. Over the last few years, we've had a huge push towards social equity and economic viability with some of these projects, right? Bringing a lot more awareness to social inequities, economic disparity, and even food insecurity. So I think the question too that I always present, how can technology, information, and innovation begin to change this design process, right? These are the same exact things I was just discussing. So how can we actually start to do that? We're left still with this kind of, again, what I refer to as a static analysis, right? A very typical condition, in this case, a large scale drawing of the Las Vegas regional area, showing in this case specific information as it relates to stormwater runoff. We have general kind of flow lines, the amount of precipitation throughout the city. And this is often kind of the standard to shoot for, right? I start to look at how can not only we begin to use, again, those same information, but expose it a little bit differently. And a lot of times this results in creating some form of animated graphic, something that can be interactive, or something that just completely changes our perspective. We can start to integrate data a little bit more into the process. So instead of just thinking about general precipitation, we can even start to see how precipitation fluctuates throughout the valley. And we can even start to think of these things not as just a two-dimensional graphic, but how can it also be shown a little bit more perceptually and three-dimensionally. The other value I think that's really important when you start to approach the use of animation in telling the story is that you still have to push that envelope of what its main intention is, right? Generally, animations are used as just showing a series of static images as a walkthrough. I approach animation as showing a series or changing in data, in this case, how precipitation changes over the years and how it starts to fluctuate at different parts of the Las Vegas Valley. And I think the last thing too, when starting this approach, is to not only think about the process as cognitive graphics like plans and sections, but also perceptually, right? So putting yourself in the same site. So, these three examples are showing, the same exact topic of stormwater runoff. Yeah, we're starting to see completely different series of information. And this is some of the work that I've been doing most recently with augmented reality, starting to show again how these different systems are interacting with each other and how they start to generate different outcomes. So in this example, just looking at more or less a pocket park, how flooding occurs on the site versus introducing things like permeable pavers, the number of trees, and showing how the resulting flooding dissipates as you start to integrate more of these green infrastructure improvements to the site. So we need to think about using this information and what kind of information is it? It's thinking about the dynamics of it. And these things can be both qualitative and quantitative. So data, like I said, has a lot of different forms, right? The whole premise that I'm preaching is whether it's tangible or intangible, like I said, out of sight, out of mind. it can be temporal, right? It can be seasonal, it can be evolving, it can even be atmospheric, anecdotal, it can be even just observational, right? So even though we start to think about data information analysis, we start to think it's all analytical, it's all numerical, it can still also be very much just through observation. And then obviously too, as we start to address some of these more critical issues of climate change and social justice, we need to have firm discussions with other professions as well. And they all typically use the scientific methods or some form of evidence-based practices. And so we can't also disregard empirical processes. And so these are the things that can start to make it be a little bit more dynamic. We have to think too how data is going to change throughout this process. So, we need to first just learn or become more comfortable in actually applying that data to the design, understanding that as we change and scale, that data also changes with it. It's not about just looking at it a little bit bigger or a little bit smaller, but how does that information actually change as we progress and scale? And something that you'll see hopefully in a lot of the work I show as well is that, analysis and design are often treated as silos. I try to really blend the two together, that they kind of create this cyclical pattern, right? As you kind of learn new information, your design changes. As your design changes, that produces new outcomes. Those things need to be validated. So it is a constant kind of refinement process. And my way of actually starting to physically do that is looking at parametric design, the idea that we have data and statistics that have variables to it. Those are going to create outputs, which help understand the performance of a space and part of a design, the same ability to measure and evaluate it. This is a big thing that the Landscape Architecture Foundation really advocates for, in understanding the difference between outputs and outcomes when it starts to thinking about integrating data into the process, is that outputs are strictly that they are just data, it's just information. It's really what you do with that information that produces outcomes, which is really what the end goal should always be. So how does that information relate to specific project goals and objectives in terms of fulfilling those needs, right? So instead of saying that the site is now only producing, or that the site's producing 5,000 cubic feet of runoff, instead of just talking about those numbers, say that it's reduced the site by 75%, or it's helped reduce flooding, right? So really kind of thinking about what the kind of, like I said, outcome is of that process. And in order to really be able to determine whether those outcomes are successful or not, we also have to have some form of baseline comparison, right? We can compare it with those pre-development conditions. So thinking about the native ecology, how current conditions or conventional development has disrupted that, and how does the actual design start to replicate or mimic some of those pre-development conditions, right? That's the only way we're going to determine whether our design has actually improved on it, by actually comparing those results. And so I find myself very fortunate that I was able to take this study from my thesis and be able to carry it out throughout my academic career and teaching for the last 10 years. A lot of people aren't able to do that. Like I said, I always pride myself in being able to have done that. And so I can't really talk about a lot of this without just starting with, some of the work that was done in grad school. And so with this topic, we were looking at the issue of a water infrastructure in a small village in Haiti, Fond de Blanc. It was about 70 miles from the epicenter of the 2010 earthquake that devastated the capital. From that devastation, it really kind of displaced a lot of the community to these outlying villages. And with that huge influx in the population, that put a huge demand on their water infrastructure. And so part of the work that was in this thesis was looking at how the introduction of a new housing development for teachers for a secondary school can start to sustainably um, harvest, collect, and reuse that water on site because it's such a challenge to attain. What happens often in this village is that people have to walk several miles just to get their necessary amount of water for bathing, cooking, cleaning. And because they have to spend so much time going out and collecting this water from different local ephemeral and permanent streams, that takes away a lot of their time that can be used a little bit more um, specifically to their education, to their daily lives, right? A lot of kids have to drop out because they have to take care of some of these other needs that aren't really apparent, right? Things that we often take for granted. And so because of that, a lot of the work did revolve around the idea of stormwater and rainwater harvesting. And so the beginning of this thesis study really began at that global scale, because if we are going to start to design for water, we have to understand the systems that begin to affect it. And so part of the thesis too was looking at how do we use different visualization and communication techniques to effectively tell the story, right? So using interactive graphics in this case. So even though these are just showing as animations, these are actually developed for the web that can be interacted with by the users. So not only having these things as animation, but giving a certain element of decision making in these graphics becomes something of interest. So the global scale started to talk about how the trade winds were affected, then the actual geomorphic processes that created Hispaniola, so Haiti and the Dominican Republic, start to also affect the rain as well, as you'll see in the next graphic. So again, telling all those elements of the story of how these things were created gives us a much more greater appreciation for the process as well. And so once we start to understand the geomorphology that created these mountain ranges throughout the island, those start to affect how the precipitation interacts with the actual site itself. And so what commonly happens in this area and for this village is the generation of these rain shadows. So we have a lot of that rain and precipitation coming on the windward side of those mountains. Those essentially capture all that rain and leave the rest of the wind on the leeward side of those mountains much drier. So even though the island itself can get around 53 to 98 inches of rain a year, this area only receives a fraction of that. So a lot of that information can be also misleading, because when you immediately hear 58 to 93 inches of rain, that seems pretty significant, but these different environmental systems can start to affect that too. And so we continue to zoom in more and more on the site. Now we're starting to look at what happens to that rain once it enters the site. We look at how the drainage lines are created. We find out that it starts to get partitioned in different regions. Some of those regions are off-site, some of those stay on site. Thinking about also how the grading is going to affect that, not only for drainage, but also the suitability for development of these housing units. Soil starts to affect what happens to that water also once it hits the site. So where is it going to have high infiltration rates versus low infiltration rates? How the vegetation starts to impact that runoff volume. And again, this element of interaction, as you start to scroll over these different regions, you start to get additional metadata within inside of that. And then lastly, once you start to actually compile all of these variables on top of each other, we get differing runoff volumes and percentages. And like I said, some of it flows offsite, which is around 50%, versus the other remaining flows to this ephemeral stream. And again, zooming in even further, now we can start to see this information a little bit more perceptually of how it starts to interact with the site. So again, looking at very similar variables, just looking at them a little bit different scale and detail of all this information. This is all being computed with standard calculators to determine what the actual runoff for this part of the site would receive. So focusing into a more specific area. And so once we start to see what that runoff volume is, we can start to see what can we do with that. And so even though a lot of my work does focus on the analytical side, the intention is for that to actually help create responsive design solutions, right? So really kind of using the analysis for a specific reason instead of just doing it for the purposes of doing it, which is unfortunately often the case. And so by regrading the sites, by using the craft of the locals and the retaining walls, we can start to utilize that water for community gardening purposes. And this work was featured in the Innovations in Landscape Architecture book, which I was very fortunate to have happen soon after graduating from grad school. One of the first projects I did after grad school was the helping and developing this guidebook on low impact development and green infrastructure for the East Tennessee region. Same idea that, you know, we wanted to really tell the story of the water resources for this part of the state and showing all the wonders that it provides, whether it's for nature, whether it's for the community, and how, you know, typical or conventional stormwater practices have really led to the detriment of these water resources. And so again, a big component of that is showing those intangibles, in this case, really focusing on the water quality issues of contaminants that start to not only affect the water itself, but can start to have long-term health effects on humans as well as wildlife. And so the guidebook shows how these conventional developments lead to some of these issues and how green infrastructure can start to alter that course. And so we, again, zoom in at different scales. So those first ones was at the development. The last one is at more of a street typology, and then zooming in even further to these elements. And at the time, you know, this was around 2013. This was something that wasn't commonly done to talk about stormwater practices, but using these section perspective drawings to show all the intangibles of these different green infrastructure components, things like evapotranspiration, infiltration, things that aren't commonly seen in the process, were important to really show how beneficial these different systems can be. And then obviously all those supplemental advantages such as creating wildlife habitat, becoming an educational opportunity. These are things too that we wanted to communicate in these graphics. Part of the process too is just learning new ways of attaining data, right? So as technology again is advancing, we're finding out new ways to get more detailed, more specific information. So one thing that's happened over the last few years is doing these workshops with drones. These drones have a great ability to create point clouds. So this is an example of, you know, not only are these just points, but they actually have colors associated. So you can get some even kind of aerial imagery out of it from these point clouds. And then what happens to those point clouds is that those can then be brought into modeling software to create some very detailed terrain models. So you can see just in this example how accurately it still captures all those little dirt bike routes. So this was just kind of a site that we wanted to study for the purposes of the accuracy. And then obviously the great advantage of that is once you get that information, then you can start to pick up with those other methods of creating different types of modeling and analysis from it. A lot of the stuff I've shown is, you know, three-dimensional, or it has a certain quality to it. Sometimes the use of parametric modeling can be used for data collection or aggregating big data sets. So in 2018, we received some funding from the Nevada Division of Forestry to look at tree benefits. So these tree benefits are, again, often things that we don't inherently, or we may inherently understand, but don't often really, I guess, understand completely, and just the dynamics of all that. So the first part of the process was, again, kind of looking at a lot of the different local vegetation and all the specific benefits provided. So things such as health and well-being, that colors, textures, response to seasonal change and blooming and wind patterns can add some therapeutic attributes for people. It can also start to create, again, outdoor comfort from evapotranspiration and shading. They can create rich and lively wildlife habitats for birds specifically. So looking at what's going to, in a plant community, help establish the main components of any bird habitat, such as the nesting component, the diet, and even the protective quality of it. So you can see all these examples we did for different wildlife. There's the cost savings that are associated with it too. And I think what's something that's really important when looking at tree benefits is that, not all trees are equal, not all trees the same. Some trees we found out are never going to save you any money. Some are going to save you in the hundreds of dollars every year. So it's really kind of interesting too when you start to realize that, there's a lot of this push on trees for their economic benefits, but you have to be very selective. You have to be very specific in those tree selections. What's also really important too is that maintaining these trees so that they're healthy is also going to affect it. Part of the study also found that there's a huge discrepancy between a healthy tree versus an unhealthy tree, which is often what happens in these urban settings when they have an average lifespan of 13 years when they should have something closer to 50 years. And so here's some examples of how, things like stormwater interception and CO2 sequestration fluctuate over time as well. And part of that process was really for the intention of bringing trees into, the underutilized spaces such as parking lots on the UNLV campus. So the students were able to take those studies of really understanding the benefits of trees and not only just say that it's good to have trees in the parking lots, but what are they actually going to do, or how are they going to affect the project site? So in this example, we see how these trees affect the stormwater runoff, and in often cases having a 100% capture rate between the trees themselves and other green infrastructure. The economic savings over the lifespan of this. So understanding too the difference between these typical or conventional design practices versus using things like green infrastructure that have a much longer lifespan is also going to save money. In these cases, you could see over 100 years, which might be a little dramatic, but it can save around $1 million. And what's, I think, really fascinating that came out of the study is that you can actually put an urban forest into a parking lot. There's this misconception that, adding trees to a parking lot is going to take away from the number of spaces. In the studies of the parking lots on UNLV campus, some may have some retained around 95% of the parking spaces. Some of the designs actually added more parking to these parking lots. And so I think what's something kind of interesting that came out of that is that we just discovered we're really bad at designing parking lots, right? And we can be much better at doing so, whether it's from this economic standpoint of, again, the cost savings associated with it, or even the other elements that, might outweigh the loss of losing a few parking spots. And so again, getting the students to understand all these different benefits that come out of just adding trees to these parking spaces. And like I said, you can see in this example really how dense some of these tree plantings can be inside of the site. And something that's also fascinating with this is that we also worked with an environmental economist from USC to determine the social implication of this too. There's some, again, other misconceptions that, adding trees to a parking lot, maybe people don't want birds living there and pooping on their car, or adding other, issues to the site. We actually found in this survey that we did with students on campus that students would even be willing to pay a little bit more in their parking fees if it meant they got more shaded parking, because typically in a lot of the parking on the campus, it's just exposed asphalt, which, considering in Las Vegas, when we get to 110, 115 degrees, can be very uncomfortable to walk to class. Like I said in that first discussion with tree benefits, is that these things can happen at different periods of time. So it was really important too to understand, when do these trees start to reach these kind of optimal performance levels? And so we actually took all that information, aggregated into these charts to really kind of determine when these things start to occur. So a scary coincidence with the economic savings of trees is that you really don't start to reach that net profit of them starting to save you money until around 13 years. The average lifespan of a tree in an urban setting is also 13 years. So what happens with that is that, even though you're planting trees, if they aren't going to last past that 13-year mark, you're really just throwing money away. You aren't really capitalizing on the whole idea of having these economic savings or benefits of trees if we aren't really advocating for their longevity. The same thing was also applied to, again, their stormwater potential. So again, it's right around that same threshold of around 12 years that they start to have a significant interception or reduction rate. What's interesting with the CO2 sequestration is that a lot of these trees are actually fairly efficient at the beginning. And that's really no surprise, since a lot of that CO2 sequestration from trees is happening from the new foliage that grows on those trees, right? So if you think about a tree as a empty canister, as it starts to sequester CO2, it's just filling up that canister, right? It doesn't actually do anything with it. It actually just retains it. And so once those trees stop growing, they start to decline on their performance. And you can start to see in this graph towards the end that some of these start to recede and start to not reach that national standard of 48 pounds a year. So with that study, we started to not only look at the trees in the parking lots, but also the trees throughout the entire campus. Out of all that study, we used around 55 unique tree species that were identified. These were the top number of trees, or the top 55 species of the tree canopy on campus, which accounted for 80% of the entire campus, and they were at around an average age of 15 and a half years. So luckily, our campus itself does pretty good with the trees that are in part of its campus core area. The campus itself is national, or it's a state arboretum. So, we take a lot of pride in our tree canopy on campus. And so this is why a lot of them are doing fairly well in some cases. And so we're using that same information that we did in collecting, their annual performance and their benefits, and started to cross-referencing that information with the tree canopy itself. And based off of that information, 36% are returning a net profit, right? So it's still kind of a small fraction when thinking about the tree benefits themselves. And so what's coming out of this study currently is thinking about really pushing the idea of what tree inventories are intended to serve, right? Tree inventories are usually developed by the city or large nonprofit entities to more or less just have that information available to monitor. I think we can use it a lot more strategically in a way that helps us really kind of hone in on what do we want our urban forests to do. It can be for a variety of reasons, right? So here's looking at what it can do in terms of the cost savings analysis. So we can see areas that are currently, again, returning that net profit. So these are the kind of areas we want to make sure we can preserve and maintain their health. These are some of the areas that are really struggling, but within anywhere between 1 to 5 years can start to also return a net profit in their savings. So this starts to identify specific areas on the campus that need to be improved on or monitored to ensure that they do reach that healthy threshold. So really kind of think about what do we do with the trees that are succeeding versus those trees that can be or have the potential to within a few years. Because like I said, it's not about just putting a tree in the ground and knowing that it's going to benefit the area. You have to really invest in it. Here's looking at that same information or that same approach with the stormwater reduction. So again, a lot of the most high performing trees are happening in this campus core area, kind of in the center. Right now, we have around 52% of those trees retaining or reducing at least 50% of the runoff on site. What's unfortunate that, overall, the trees on campus are only reducing the entire campus runoff by 9%. And that's because we haven't strategically placed these. A lot of these trees are in like I said, the campus core where we have large grass malls, a lot of softscape, but the major contributors to the campus are large expansive parking lots, which don't have a lot of trees. So we need to think about if the stormwater runoff is a real issue, we need to start to put those trees specifically in those strategic locations. Here we can see those areas that, again, within 5 years can also reach those thresholds. And this is where we start to encroach on some of those parking lots. You can see in the top image, that was the example of the student study that found contributed a lot to those runoffs. And now we start to get towards some of those other outlying parking lots. Like I said, the trees do really well with the CO2 sequestration. We're at that 65% threshold of that national average of 48 pounds. We can see that, these are some of those areas that within, again, that same time frame, this is another additional 27% that can also start to reduce it. And, this is an important statistic to think about for this area, considering where this campus is located. So for any of you that aren't familiar with the Las Vegas area, the UNLV campus is about 2 miles from the Strip. It's kitty-cornered from McCarran International Airport, which receives around 52 million visitors a year. So we have a lot of air traffic that comes to this area that's nearby. Oh, excuse me. And we have a lot of visitors, excuse me, from California that come. So we have a lot of the CO2 emission that's nearby on the campus. The campus itself is a commuter campus, meaning a lot of the students are driving from the other parts of the city. So that's why we have also so many parking lots. We can even start to, look at those statistics with these charts to begin to really kind of think about where are these trees in the process? What are their projections to get to these significant thresholds? This is all information that can be used to work with the campus architects and grounds and maintenance crew to develop strategic plans to ensure that our trees are going to reach those pivotal benchmarks and can really start to improve on those campus conditions. So a lot of this, research and information and projects have resulted in a recently accepted book publication with Routledge, where I'm actually going to start to show the methodology of doing these things. So this is a really exciting benchmark that I just hit, in going over these things. And so the main purpose of this book is to really think about how do we take things that are conventional, whether they're climate tables and diagrams, whether they're these abstract calculators that are online, how do we start to actually tie these into the actual site itself, right? All these things are very abstract. They're all detached from the site, which is what we're trying to actually design for. And how do we start to physically integrate these? So you're actually getting a little bit of a sneak peek on some of that work that's going to be in that book in May of 2022. Some of these things, aren't complete novel ideas, which I think is important, right? We're trying to use industry standards and methods that have been accepted by the Landscape Architecture Foundation, which recently came out with a guidebook on using these landscape performance calculators and methods, and literally just starting to model it. So I've actually been working with them quite a bit to find specific methods and calculators that they feel would be great to actually visually show through these modeling techniques. And so the majority of it is going to use parametric modeling, so Grasshopper and Rhino, to generate these outcomes. And so it is going to be also an instructional book where it'll take you through step-by-step instructions on recreating these scripts, right? So these are fairly advanced and complex, but the good thing is that it really does walk you through that process. And even though these are going to be advanced, they still utilize the foundation of those inventory elements, right? It just starts to, again, show that relationship and how these things start to interact with each other. And so this is actually something that I did back in 2016, so it's a little outdated, but it is going to get a rebuff for this book publication. But I think this is something, again, going back to what I was talking about at the beginning of this presentation and lecture, is the kind of part of the site analysis with using concentric circles for mapping out distances, which I think is very convoluted and misleading, because those concentric circles really just show the shortest distance in a straight line. And you can see in this example how if you want to access certain areas, that they often aren't nearly as close as that concentric circle might indicate. So, we have to really think about those shortest path on using actual routes, such as roads or pathways. And that can even, increase those distances by 50% or even 100%. So using things that can be a little more accurate, since we are using very advanced data information. This example, we can see how we can begin to model erosion potential. Although, the book isn't going to have animations, these are things that can be animated to show progression and processes, in this case, ecological succession, so planting for wildlife habitats. Here's another example of stormwater runoff, showing how different surface types and the size of these surface types contribute to runoff volume. This is one of my favorite pieces of work that's going to come out of this book, is showing these shadow hours. So in this case, we can actually start to see which areas get the most hours of shade. So instead of just, kind of overlaying several shadow projections to show something a little bit more qualitatively, we can actually start to quantify these things too. So we can even get more specific when running these shade studies of actually finding the hottest days of the year. So what also kind of drives me nuts is that a lot of these sun studies are always done for, like the summer solstice, where it's the longest day of the year, but it's not necessarily the hottest day of the year. And I think that's what's more important to do these shade studies, is actually provide cooling for those really extreme temperatures. And even though this doesn't show it, the shadow patterns for July 3rd aren't that different from the summer solstice, yet the temperatures are around 10 degrees different. Here's an example of, again, looking at those wind conditions, right? So instead of just showing wind direction on a site, we can even start to compare how do trees start to affect this wind envelope. So depending on the size and height of these trees and the direction and speed of those winds, those are going to create different wind projections over that. So thinking about them serving as some type of windbreak. Another recent project that's coming out of this is a USDA funded grant that's looking at food deserts throughout Las Vegas. And so we're actually using, again, this process of overlaying a lot of data and information to really refine food deserts in Las Vegas. And, it's a really important topic to address, considering, almost 25% of the US population lives in a food desert. We look at the definition of what a food desert is. Again, big things with low income, census tracts, and low levels of access. When thinking about Las Vegas more specifically, since a lot of these distance calculations are looking at around half a mile or a mile, I don't know about you, but when it's 110 degrees, I'm not going to be willing to walk half a mile to go get fresh food. I probably won't even walk a couple 100 feet to get fresh food. So, things that aren't often considered in these methods are even the contextual environmental conditions. So that's some of the other additional variables that are being introduced. So, like I said, we're trying to redefine what a food desert is specifically for Southern Nevada. These are some of the variables, and working with students and our collaborators are to also include in that process. And so, we're just using a fairly standard linear combination method of mapping out every single variable, assigning it a rating system. And so you can see these are just some examples of these rating systems, looking at things such as those demographics, land cover, point data. Those are all resulting in an overall rating system of areas that are struggling the most with access to fresh food. The intention of this is that once we've refined and gotten these maps to their final result, is that we can then go to these specific communities and work with the neighborhoods themselves. So working with nonprofit organizations, working with the community members themselves, and start to provide them training on planting trees in these areas. So giving them fruit and nut trees that they can take back to their home to start to alleviate that strain on access to fresh food. And what's also going to come out at the end of this study is strategic maps for each municipal area within the region. So that way policymakers and decision makers can actually be given the, the floor plan to do future improvements. And so the last thing I'm going to show is how a lot of this information can even be done through augmented reality. And so I think it's really important to think about why would we want to use augmented reality? What are the benefits and potential? The ability to merge and integrate these things. I think there's a really fascinating aspect of this kind of participatory engagement where we can start to actually get a lot of people interacting with it that aren't necessarily landscape architects, but just the general public. And then that ability to, again, show those intangibles. These are some of the processes of how it can start to be done and the byproducts as well. And so here's some examples, just starting kind of with the main elements of it. So thinking about with AR and this design process is that you can think of, there's an element that's the actual game board, right? So it can be kinetic sand, it can be a flat piece. In this case, we're using Xbox Connect to use this point cloud to essentially overlay a digital model with a physical model. Then we have game pieces themselves, which use these Aruco markers that allow us to essentially used as game pieces. So in this video example, I'll play that again. As I'm rotating the piece, it changes the size of the tree, which is then going to affect other elements in the design. So it's a little bit laggy, you know, it's all kind of in this beta testing process. So still some things to work out. The one, you know, I think most valuable part of this is that we're using a specific augmented reality software that integrates with a modeling platform, in this case, Rhino, again, an industry standard software. And you can see these side-by-side comparisons of actually using a smartphone and the AR app where I'm physically placing these kind of basic elements of trees, benches, and pathways, and actually being there out on the site at a full scale and placing these in. And then it actually simultaneously syncs with a 3D model to create something to improve on, right? So the AR really gives us kind of, again, the wireframe aspect of the design. But once we've kind of placed that, then we can actually make more specific detailing and refinements to it so that they actually are starting to work with each other. And what's cool too with the AR app is that you can actually, once you place these, you can still continue to interact with them and change sizes and placement of these objects. So once you even place these in, you can think about these can lead to clay model renderings that you can then take into Photoshop and refine. They generate this line work, which can then be transformed into line drawings, right? So there's a really kind of nice synergy that's happening with all these different programs and applications, so that it's not just, again, dedicated to your smartphone device, but it's actually going into software that we typically use for other design purposes. So not only are these things, again, just qualitative, but now we can start to integrate a lot of that data that was shown earlier with tree benefits. So actually linking in the performative aspects of trees. So not only just placing trees, but thinking about what can they do to contribute to improve on a space as well. I'm going to speed up some of these for the sake of time, but you can see that what's great is once you place those trees based off those markers, then you can start to move sliders to change their size or their age and see how those benefits change as well. You can start to change the type of benefits, so whether it's stormwater, CO2 sequestration, we have property value, and also air quality. Here's another example. Oops. Here's another example of that game board piece where, you know, we're starting to analyze these landforms a little bit more. So here's where I show how it's all connected to that Xbox Connect and starting to analyze the erosion potential of the site. So even as we start to change our landform itself, so again, skip ahead a little bit. So starting to alter that landform. And now we get new results from that. And we even get some statistics coming out of it as well. And so this goes back to that idea again of, you know, what you're doing on site in real scale, but now it's also embedding that data to it. So instead of just thinking about walking paths and trees, what are these going to do for cost savings? What are these going to do for stormwater reduction? So in addition to that, you can see these in the AR video app. There's the cost savings that start to happen as we place things like permeable pavers on the parking lot, as we put grass and lawn in the space, what those savings are going to do, what they're going to do for runoff reduction. So again, we have a lot more that's part of this decision-making process. We can think of them as kind of even just these thumbnail diagrams to do some fun exploration. Again, these can help with, you know, being treated as decision-making tools that can be changed and manipulated to move benches based off of where the shading is, how trees are going to affect different runoff. Here's a series of these different kind of, again, thumbnail diagrams that we start to use for the AR application. Here's students actually applying this. And so in 2020, Um, I was given the honor of being the Garvan visiting professor at the University of Arkansas. So this was, again, in fall 2020 when things were still remote. So I was actually teaching these students that were in the University of Arkansas all remotely. And so, the actual process and the modeling can be attained, considering especially that these are only second year students, in getting them to actually learn this process and start to play around with these techniques. And you can see too with the performative aspect that you can start to evaluate different scenarios based off of the slope conditions, the number of trees, and how they affect runoff volume. And this is also part of a internal grant to actually create this AR sandbox that we can take to places like public libraries or other events to have other people learn about it outside of our discipline and our profession. And the ultimate goal is to kind of thinking about when we start to integrate data, we can start to create a variety of different scenarios and different options, right? Going back to that idea of divergent thinking instead of having a preconceived idea. So thinking about solutions, understanding that design, there's no silver bullet solution, something that's going to fix everything. So it's really about kind of finding a solution that's best for the purpose. And so, I always like to leave off for thinking about, all this was about storytelling. So hopefully this inspires you to think about